Yeah, I'm gonna admit I should have known that was going to happen. That quiz did not go too well. But there are going to be quizzes in the future, and it's good to know that I don't know linear approximation. I have a slightly better understanding of it now, so I'm going to go over it before I go over anything else today. Heck yes, this orange marker works. It is an absolutely disgusting color, but we make do. So let's say, for the sake of example, that we're given this multivariable function, x times e to the xy power. And we are asked to approximate its value at the point 1.1, comma, negative 0.1. Now, as I said yesterday, plugging this thing in directly to the function is extremely funky, so let's approximate. We know that this is the equation for the linear approximation of a value at a certain point. But the thing that was tripping me up is I had no idea what a and b were. We know that x and y are 1.1 and negative 0.1 respectively, but a and b aren't really defined. A and b, it turns out, are two numbers that are just close to the values that we're trying to approximate with. And we want these numbers to be relatively easy to work with. So for a, I'm going to set that value equal to 1, and for b, I'm going to set that value equal to 0. Now remember, we want these values to be very, very close to the values we're trying to approximate, because the further away you get from this point, the less accurate your result becomes. But these values are both only 0.1 away from the desired value, so that's going to serve our purpose as well. We find our partial derivative with respect to x. I made a mistake here. X is not constant. Let's actually compute the partial derivative with respect to y now. There we go. Let's start with our partial derivative with respect to x, and plug a and b into it. We get that the partial derivative with respect to x at 1, 0 is equal to 1. Let's do the same thing with the partial derivative with respect to y, and we get that the partial derivative with respect to y at 1, 0 is also equal to 1. Lastly, we plug 1, 0 into the original equation, and surprises of surprises, we get that that is also equal to 1. With those values in mind, we put what we just found into this equation. F of 1, 0 is equal to 1. The partial derivative with respect to x at 1, 0 is also equal to 1. Our value for a is 1. Our value for the partial derivative with respect to y at 1, 0 is also 1. And our value for b is 0. Plugging everything in, this is what we get. Let's simplify a little. We get that the value of the function f at these 2 points with respect, we get that the linear approximation of the function f at the point 1, 0 is going to be equal to x plus y. And since the point that we're looking for is sufficiently close to this point, we can plug this directly into this. A lot of ones in this particular problem. The approximate value of this function at 1.1, negative 0.1 is 1. Plugging this into an actual calculator gives us that this is equal to 0.98542, which, as you can see, is really close to 1. Hence why linear approximation works. Freaking awesome, dude. I make a triumphant return to physics. It feels like I haven't studied physics in a while. I haven't really learned anything new, actually. The midterm was last week, so we didn't really learn anything that week, because we did a review session before the midterm, and we're just introduced to new stuff on Monday. So let's do some new stuff, shall we? We started on capacitance. Capacitance is a unit that is in terms of charge over voltage. If you have two oppositely charged insulators and you place them a distance apart from each other, you are going to create a potential difference across those two insulators. And depending on that potential difference created and the charge of your insulators, you are going to create a capacitor. The most common type of capacitor that we are going to run into is a capacitor with two charged plates placed some distance apart from one another. The general equation for capacitance in a capacitor of this type is epsilon naught times A, all divided by D. We notice that as the area increases, so does the capacitance. Inversely, as the distance between the two plates increases, the capacitance decreases. That'll buy. But capacitors can get much more funky than that. But let's table that thought for a moment. And talk about symbolism. No, not the type that Ernest Hemingway loves to use. In circuitry diagrams, this is going to be your symbol for a capacitor. And this is going to be important, because it allows us to see which way that our capacitors are placed. Because there are two major situations which we are going to need to be acquainted with. When you line your capacitors up in series, you are just lining them up along the same path. Your current runs through one capacitor, and then into another, and then out of the system. But there are a couple of things that we know about capacitors in series. We know that when capacitors are lined up in series, the charge inside those capacitors are going to be equal. The charge in this capacitor here is going to be the same as the charge in this capacitor here is going to be the same as the charge in a capacitor that is a million capacitors down this path. Charges for capacitors in series are always the same. Potential, on the other hand, is a different story. Since these capacitors are running all along the same path, we know that along that path at the point A and the point B that there is going to be a potential across it. But since these capacitors are all on the same path, the potential from A to C and the potential from C to B need to add up to V. V, the potential across the path, is going to be equal to the sum of all the potentials. But there are also ways to simplify down systems of capacitors. If we say that the capacitance in this capacitor is equal to C1, and we say that the capacitance in this capacitor is equal to C2, we can distill the essence of this capacitor system down into one equivalent capacitor. Since they're in series, we're still going to have the same charges, and since capacitors do not affect the amount of voltage that is being supplied to the system, the voltage also stays the same. But what would the equivalent capacitance of this gigacapacitor be? Let's do some math to find out. Let's keep our equivalent capacitor up here, and our original capacitor system down here, because this is the thing that we're going to be focusing on for the time being. We are given the capacitance in this here capacitor. And we know from the definition of capacitance that the capacitance inside that capacitor is going to be the charge inside the capacitor divided by the potential difference acting across the capacitor. And we also know that since this thing is lined up in series, that the charges inside these capacitors are going to be equal. Therefore, the charge inside capacitor 1 is just going to be Q. To determine the equation for the capacitance in capacitor 2, we use much the same logic. Next, we know how to find the potential difference acting across this first capacitor. It is simply going to be the potential at C minus the potential at A, which we know is going to be greater than 0, because as we are moving from A to C, potential is decreasing. We use the exact same logic to find the potential difference acting across the second capacitor. And we also know that the potential difference across the entire system is just simply going to be the sum of the potential difference across the first capacitor and the potential difference across the second capacitor. The total potential difference must be the sum of all the voltage drops. From all that, we know that the capacitance in this equivalent capacitor up here is going to be the charge in one of the capacitors divided by the potential difference across the entire system. But what we want is an equation for the capacitance in this equivalent capacitor in terms of the capacitance in the capacitors of the equivalent system. But what we want is an equation for the capacitance in the equivalent capacitor in terms of the capacitance in the system of the original capacitors. So we recall that the potential difference across this capacitor plus the potential difference across this capacitor is going to be the entire potential difference. Then we recall our equations for each capacitor, and we solve all of these equations for the potential difference across each capacitor. Then we notice that we can substitute each one of these back into this equation. We get that Q over C1 plus Q over C2 is equal to Q over C12. The Q's all cancel out. And this is what we're left with. This is one of the golden rules for capacitance. The capacitance of an equivalent capacitor for a system of capacitors in series is simply going to be the inverse of the sum of the inverses of all the capacitors. And we can use this for any situation as long as our capacitors are in series. To reiterate, for a general situation where we have a system of capacitors in series, there is going to be equal to the sum of all the inverses of the capacitors in that series, inversed, adding up a bunch of fractions and then flipping them over. And mathematically, this means that the equivalent capacitance for a system of capacitors in series can never be larger, actually, than the capacitance of any of the capacitors in that system. The potential difference across that system of capacitors is going to be equal to the sum of the potential differences across all the capacitors. And the charge in every single one of those capacitors are going to be equal. Bam, capacitors in series. The next major situation that we need to become familiar with is when we have capacitors in parallel. Instead of our capacitors being lined up in a straight line, they are along their own separate branching paths. Current no longer needs to flow through one capacitor to get to another. The first difference besides structure that we have from capacitors in series is that the potential difference across one capacitor is going to be the same as the potential difference across another capacitor. Something else is going to need to change if voltage remains constant, and the only other variable available is charge. So charge is changing depending on the capacitor, which means that the charge inside an equivalent capacitor for a system of capacitors in parallel is going to be the sum of all the charges inside the capacitor, which means that the charge inside an equivalent capacitor is going to be equal to the sum of all the charges inside of all the capacitors in our system. And this right here is where we derive our golden rule for capacitors in parallel. Because using basic algebra, we can discover that Q1 is equal to C1 times V1. We got that from our definition of capacitance equation. Using the same logic, we get a value for Q2. And the charge inside the equivalent capacitor is going to be the equivalent capacitance multiplied by the potential difference in the system. Much like before, we plug this into this. We get C12 times V is equal to C1 times V plus C2 times V. The V's cancel out, and we get that the capacitance inside an equivalent capacitor for a system in parallel is just the sum of all the capacitances, which is kind of awesome. So if you put multiple capacitors in parallel, you are basically creating a big capacitor with a larger capacitance. Lastly, for physics tonight, let's very briefly talk about dipoles. A dipole is a system of two oppositely charged particles separated by some distance d. That's literally it. That's all that a dipole is. But as always, it gets more complicated than that. Let's imagine that we slap this puppy in an electric field. What the heck is going to happen to it? Well, I'll tell you. At the positive part of the dipole, there's going to be a force acting that way. The force's magnitude is going to be equal to the charge of the particle times the intensity of the electric field. And at the negatively charged end of the dipole, we are going to have a force acting this way, also equal to the charge of the particle times the electric field. We know from statics that if the sum of the forces is equal to 0, then this thing isn't moving. So this thing isn't going to be seeing any horizontal or vertical movement. But remember, movement in a straight direction isn't the only thing that we're worried about. Because, oh yeah, couples are here! We have two forces that are equal in magnitude acting in opposite directions some distance d away from each other. Right about now, I'm feeling really glad that I'm taking statics at the same time as physics. The course material has lined up scarily well. I hope that it's going to continue this way. Knowing my luck, it won't. So a dipole in an electric field is going to create some torque. First, let's define a position vector between the two particles. And we also know that the magnitude of the moment of force is going to be given by r times f times sine of the angle between them. And we can apply this exact same logic to dipoles in an electric field, just by doing this. The torque is just going to be the cross product of the position vector with one of the force vectors, which of course we can write as d times f times sine of theta. Lastly, we can find the potential energy in one of these dipoles, because we know that the potential energy is just going to be the change in work, and we know that torque is going to be decreasing while theta increases. So this is going to be equal to the negative change in potential energy. Okay, so I did some reading, and it turns out P is not the position vector. P is a moment created due to the charge and the distance. We can write the distance d as a vector and multiply it times q to get this moment vector. With that clarified, let's go back to what we were originally doing. Since we know that this is equal to negative du, we can write the potential energy in a dipole as negative p times e times cosine theta, which we recognize from Calculus 3 as being the dot product. It's insane how all these classes are just fitting together this semester. I would have never suspected that they would. I was probably supposed to take some of these classes before some of the others. That may be a story for another day. But now, very quickly, I want to share something I learned in statics. First, let's talk about equilibrium in a body with two forces acting on it. This body has only two forces acting on it. We're neglecting weight, and yet it is in equilibrium. We know that a line runs through the points of application of both of the forces acting on the body. From converting these forces into their force couple counterparts, we find that the line of action for both of these forces is the same, and that it runs through both the points of application. Something a little situational that I have had to use on this past week's homework. Next, a little trick that I learned about solving static systems in 2 dimensions. Let's say that we want to find the tension in both the cables holding up this beam at an angle. And we want to find the angle theta that the cable CD is positioned at. It seems a little bit dubious that we can do this problem at first, especially the angle part. I mean, it would be pretty much impossible to draw like imaginary triangles to get this angle. But there's something cool that we can do, that I'm going to need to draw this larger for. One larger drawing later. Okay, we know that all these forces are going to have certain directions and certain lines of action. I'm going to draw this force a little steeper, just to illustrate the point. As you can see here, all these forces have certain directions. If a body is in static equilibrium, then we know that there needs to be a point somewhere where all the lines of action of all the forces intersect one another. We can draw out the line of action for the tension in cable AB. We can draw out the line of action for the weight force. And we can draw out the line of action for the tension in cable, and we can draw out the line of action for the force in cable CD. And as you can see here, they all intersect at this point. We'll call it E. Furthermore, there is a second point that is directly below point C. We'll call it F. And we also know that the distance from B to the point of application of W is going to be the length of this thing divided by 2, which means that we can use trig in order to find the length of this, and from there, it's just geometry to find the angle theta. The impossible becomes possible through learning. Lastly, for statics, I want to go over what I think we are going to learn tomorrow. We recall how last time we were introduced to this monstrous system of equations. Remember, feasibly we could solve for 6 unknowns using this. But, I'm gonna be frank, this is a pain in the ass. But it don't have to be no pain in the ass. Damn it with the double negatives. Because using force couple properties, we can resolve everything in that messy, messy problem into one beautiful set of force equations and moments about a single point. That means that we could potentially completely eliminate 3 unknowns. One in the x direction, one in the y direction, and one in the z direction. Which makes our lives so much easier. We can start by taking the sum of forces and setting them to 0. We take all the forces in the x, y, and z direction and throw them in their own equations. This is basically the same thing as saying the sum of the forces in the x direction is equal to 0, the sum of the forces in the y direction is equal to 0, and the sum of the forces in the z direction is equal to 0. But that wasn't the difficult part. The difficult part was the moments. So what we do is we pick the point in the problem where we have the most unknowns, and we take the sum of all the moments in the system about that singular point, which, as I studied over the weekend for the statics midterm, which I think went pretty well, but I digress, is going to simply be the sum of all the cross products of the position vectors from the point to the point of application and the force vectors. And this, of course, in a static situation is going to be equal to 0. So we reduced 6 equations down to 2, which, in my book, is a lot easier. So I think I'm ready for class tomorrow. That'll be it for statics tonight. Let's see if I can do some citizenship and public ethics. It's been a while, and admittedly it's been a while since I've covered my public policy class. Admittedly, it's been a while since I've last covered citizenship and public ethics, so there's quite a bit of material that I need to go through. It'll just be a quick rundown. I don't need to write this on the board. I don't need to write this first part on the board. There's a difference between checks and balances and separation of powers. Checks and balances in the United States were created so that one branch of the government would not hold more power than the other. There are various actions that each branch can take to keep the other in check. For example, a president can veto any bill passed through Congress. Or Congress can impeach a sitting president. Or the Supreme Court can rule that a law passed is unconstitutional. Separation of powers, on the other hand, ensures that each branch of the government has different responsibilities within that government. For example, the legislative branch has the power to declare war, the executive branch conducts diplomacy, and the judiciary interprets the Constitution. Different powers, different responsibilities. The next big topic that we are covering are the 3 different theories of citizenship. They outline what they think the most important aspects of society and democracy are. We've learned the first 2 so far. The first is liberalism. Liberalism emphasizes personal liberty, states that citizens can make informed decisions based on their own self-interest, and that state power should be limited and dispersed. Citizenship overall is a formal legal status where the same rights are granted to all citizens. Also, the exercising of one's rights, like the right to vote, is a personal choice. For a person who follows this school of citizenship, choosing not to vote is just as valid of a choice as choosing to vote. The next theory is civic republicanism. Civic republicanism emphasizes participation and states that consensus can be reached through open deliberation of issues. And based on that consensus, citizens can move towards the future. Those are the 2 that I've learned so far. It's getting pretty late though, so I think I'm not going to go over examples of them both tonight. That will be a future issue. Plus, I have recorded so far over an hour and a half of footage, which is going to be a nightmare to edit. But that's not something y'all need to worry about. And we should be celebrating. It's a good night. I got through the material from 4 classes tonight, which is great. And I know that if I can keep doing this, that this semester's gonna end up great. So, that's gonna be it for tonight, ladies and gents. Thank y'all so much for watching. See you tomorrow.